Hello again. I'm here with a video related to doing acceleration analysis using the relative motion method. So our objective is to do acceleration analysis using relative motion method. So the first question probably comes to your mind is, can we do acceleration analysis using, for example, the ISEE method? And the answer is yes, but the IC method is very easy for the velocity analysis. And the instantaneous center that you find for zero velocity is only good for velocity analysis. There is a point also known as instantaneous center of zero acceleration, but locating that point is not easy actually. So that's why this method is basically forgotten, because it's not a robust method, it's not easy, it's not a shortcut. IC method definitely for velocity analysis is a shortcut. Of course, you have the choice of using absolute motion, but remember, absolute motion is a method which is more mathematical, and it's in a way limited. You can't use it for every problem. In any case, so we are basically limited to just a relative motion approach, and that's what my objective right now, to discuss this particular method. Okay, so this is pretty much like relative velocity analysis using relative motion. The approach is exactly the same. There is only one thing that you have to be careful with, and I'm going to mention this in a few minutes. Okay, so now we could say that for a body in general plane motion, again, I keep repeating myself in other videos, but I just want to make sure that everybody understands. General plane motion means what? Means a body that is partly moving, having a motion that is part translation, part rotation, like motion of a wheel, for example, as it rolls, or the motion of the connecting rod in a crank slider mechanism, and many other examples. All right, so now, if we have acceleration of one point on the body, so this is for what? For a given instant. So at a given instant, if we have acceleration of one point on the body, for example, acceleration of point A, okay? So say acceleration of A. Also, if we know omega and alpha of the body, okay? Then, just like when we did the velocity analysis, we should be able to find what? Acceleration of any point on this body at this instant, say acceleration of B. So the objective now, let's say, is to find absolute acceleration of B. How do we go about finding acceleration of B? And as I said, this is just like velocity analysis. So we say, okay, you want to find acceleration of B, no problem. Why don't you use A as your reference, accelerate with translate rather with respect to A, and then add the rotation part of the motion to it. And then remember, this part means rotation about point A. And then the sum of these two terms will give you what we call acceleration, or absolute acceleration of point B. And that's what we're looking for. What is the actual acceleration of point B? All right, so you guys remember, for velocity analysis, this part is what? Acceleration of B relative to A means find acceleration of point B as if A is what? Fixed. We know A is not fixed. A is moving with some acceleration. But what if we made it fixed, like in this picture? Now, what you have to be careful is, unlike velocity, where velocity of B relative to A, for example, was simply just R omega, or omega cross R, if you wanted to do it vectorially, which is not, by the way, advised. I'm not going to do it vectorially. It doesn't make sense. It's not worth it. Even though, like in the PowerPoint slides that you see, they do actually use the vector approach, and you also see it in the solution that you for these homework problems. In any case, remember that when a rigid body is in pure rotation, there are two components of acceleration. So this is not pure rotation about A. This is this part of the motion. So there are two components of acceleration, normal and tangential. Normal always points toward the center of rotation, toward this point A, and tangential follows alpha. That's why it's pointing down. Because this body at this instant is accelerating, it's rotating clockwise and actually accelerating. That's why alpha is also clockwise. Okay, so then the acceleration of B relative to A, then it becomes the resultant of these two components, A and AT. But actually, we never actually, we don't really actually find this guy. And you'll see in an example in the next video. Let's move to the next page. So remember now, the normal component of acceleration is R omega squared, and the tangential component is R alpha. And then if you want acceleration of B as if A is fixed, it becomes the square root of AN squared plus AT squared. But as I said, we just leave them alone as components because eventually we have to break the our final equation into components, horizontal and vertical. So basically, you never really get this part. You don't do this part. Anyways, so back to our equation here, acceleration of B is translation part plus the rotation part, acceleration of B relative to A. If you add acceleration of A plus the rotation part, which I have it in the other picture here, kind of this guy, right? Of course, they're not to scale. So if this is the rotation part of the motion, then when you add these two head to tail method, you get what? You get acceleration of B. So at this instant, as this body going through combination of what? Translation and rotation, acceleration of B. This is absolute acceleration of B. Now, recall that you could actually do this vectorially just to let you know that, for example, AN is omega cross V, or you could also write it as minus R as a vector, omega squared. These are vector. The same two terms that I have them in the scalar format. If you want to do it by vector, AN is omega cross V or minus R omega squared, and A sub T is alpha cross R. Again, I don't recommend you guys do the vector approach. The scalar approach, in a way, is much easier. By scalar, I mean you find the magnitude and you put the direction next to it, like direction of acceleration of A. Anyways, now, because of the next problem, the next video, I'm going to put it in the sequence for you for next week. The week of, I believe, March 30th, yes. I'm going to start actually with the rolling motion. I just wanted to give you a heads up for a rolling motion. You guys already know that this point is the instantaneous center of zero velocity. But that's not the point of instantaneous zero acceleration, by the way, as I discussed in the previous, at the beginning of this video. Yes, velocity of A, which is the center. Now, A is the center point, center of this wheel, which has a radius of R, right? Velocity of A is R omega, no problem. That's velocity of A. And it's 90 degrees to this radius. But only for the center point, not any other point, like not a point like this, like B here. Doesn't work. Okay, so be very careful, guys. Only for center of the wheel, it could be shown that velocity, acceleration of A, I keep doing this mistake, by the way, it happens in every video. I have the eraser and then I keep using the eraser. Anyways, let me put these back for you so you could see. Okay, acceleration of A becomes R alpha in the same direction of alpha. You see how this body is physically rolling or rotating clockwise and actually accelerating. If alpha and omega are in the same direction, that guy is accelerating. Acceleration of A would be also, just like velocity, 90 degrees to this radius. But only for what? For the center of this disc or wheel. Alright guys, so be very careful. I'm going to now show you an example in the next video related to the rolling motion, and you see what I mean by not using the actual square root of an squared plus at squared and leaving these guys in the individual form. Okay, as always, thanks for watching and listening.